In this lecture, we will discuss the fundamental theorem on linear maps. What is fundamental theorem of linear maps? Suppose V is finite dimensional vector space such that T is a linear map from V to W. Then it says range of T is finite dimensional. Okay, when T is a linear map from V to W and V is finite dimensional, then range of T will be finite dimensional. And second, it says that dimension of V equal to dimension of null space plus dimension of range space. Okay, it's called rank nullity theorem. Rank nullity theorem. Okay, so we will prove both these statement. It is very important, so please watch this video till the end. Okay, now we will prove that first it is a finite dimensional range space is finite dimensional, and then we will prove that rank of T plus nullity of T equal to dimension of V. So since null space of T is a subspace of V, but we know that it is a subspace of V and V is finite dimensional, so subspace will also be finite dimensional, hence null of T will be finite dimensional. Okay, so assume u1 u2 dot um be basis for null space of T. Okay, assume this is a basis. Okay, this is a basis for null space of T. We will use this basis, okay, as null space of T contained in V. So u1 u2 dot um are member of null space of T, so member of V. As it is basis, so it will be Li. So u1 u2 dot um are Li vectors of V. So by extension theorem, what we can say is that any linearly independent set of vectors can be extended to form a basis of V. Okay, so this is linearly independent set of vectors in V, so it can be extended to form a basis of V. So assume we have extended this linearly independent set to form basis of V. So assume u1 u2 dot um, and we have added some extra vectors like v1 v2 dot vn. Okay, and these vectors forms basis of V. Okay, u1 u2 um comma v1 to vn forms basis of V. Okay, so here dimension of V is m plus n. We have m plus n vectors in basis. If we show, okay, we will use these statements. If we show dimension of range space is n, if we are able to show this statement, then we are done, because what we know that dimension of null space of T is m, because basis has cardinality m. Okay, this is a basis, so we can say that dimension of null space of T equal to m. So dimension of null space of T is m, and dimension of range space will be n. Then it will be dimension of V, because dimension of V is m plus n. Okay, so we are trying to show that one. We will prove range space of T is finite dimensional firstly. So let V belongs to V is an arbitrary element. We have taken any element from vector space V. So V can be written as C1 V1 plus dot CM VM plus D1 B1 plus dot DN VN. Yeah, for some scalars, for some scalars, Ci is belonging to field and Di is belonging to field. I vary from 1 to m, and here J vary from 1 to n. Okay, so B can be written as, because this is a basis, we have extended u1 u2 m to b1 b2 bm. Now taking both sides as t, a linear transformation, what we have, T of B equal to T of C1 U1 plus Cm Um plus D1 V1 dot of 2 Dn Bn. Now using the linearity of T, what we get is C1 V1 plus C2. Here it will be dot 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 here. Okay, plus C2 V2 plus dot dot Cm Um, not V2, that will be U2 plus Cm plus D1 V1 plus dot Dn Bn. Okay, we have used here linearity of T, but what we know that U1 U2 Um is a basis for null space. So by the definition of null space, any element has image 0, then that element will be in the null space. It means T of U1 equal to 0 dot dot T of Um will also be 0. So these elements will be 0, and say resultant what we get is T of B equal to D1 T of B1 plus dot dot T and Dn T of Bn, because remaining vectors are 0 and resultant will be 0. So 0 plus this vector will be these vectors only. So we can say this is the arbitrary element of range space of T. Okay, this is arbitrary element. So it is spanned by T of V1 dot dot T of Vn, and say we can say that this is a spanning set for range space of T. Okay, now we have proved in my previous lecture that linearly independent set has cardinality is less than equal to a spanning set. Okay, so cardinality of a spanning set is will be greater than equal to cardinality of linearly independent set. I have proved in my previous lecture. Please watch that video if you do not know this statement. So this is a spanning, and subset of this will be linearly independent and also be a spanning. Hence that will be the dimension of range space of T. So dimension of range space of T is less than equal to n. Okay, so now we'll prove that this is Li, T of V1, T of V2, dot dot T of Vn is Li linearly independent. So let for some scalars C1 dot dot to C n belonging to field such that C1 T of B1 plus dot dot Cn T of Bn equal to 0. Now if we use linearity, what is linearity? T C1 V1 plus C2 V2 will be C1 T of V1 plus C2 T of V2. So we are given this one, we will write this one in the place of this. Okay, so we can write like this using linearity. And what we know that if image of any vector is 0, then that vector will be in null space. Okay, and also know that u1 u2 dot dot um is a basis for null space, basis for null space. So if this element is in null space, this is a vector. Okay, linear combination of vector is again a vector. So this is in null space, so we can have a linear combination of basis element for some scalars. So this vector can be written as d1 u1 plus dot dot dm um for some scalars d1 d2 dm. If we take this element in the left side, we will get this C1 V1 plus Cn Vn minus D1 U1 minus D2 U2 dot minus Dm Um. But what we know that U1, U2, V1, V2, Vn is a basis for B. Remember, we have extended U1, U2, Um to V1 to Vm to form a basis of V. So since this is a basis, this will be Li. This is Li, linearly independent vectors. It means their coefficient will be 0. So C1 equal to 0, dot Cn equal to 0, and this also be equal to 0. And see what we have proved, that this is Li, and we have also proved that this is a spanning set for range space of T. And say the simple dimension of range space of T equal to cardinality of basis, cardinality of basis, and which is n. So we are done here. Okay, thank you for watching this video.